All right. Well, let's go ahead and get started. So what we'll do today is I'm going to give you the solution of the homework assignment, and then I'll give you a new homework assignment that's finding 2 online now. So there's a new homework assignment that will exercise some of the other addressing nodes. So it's it's kind of a similar in terms of nature of the homework assignment. So you just kind of have to use the same approach a little bit differently, but almost the same kind of approach. So the first thing we'll do is to finish up the homework assignment that was due today, like 2 minutes ago, and then we'll talk about the new one. And then after that, we'll move on and talk about the add instruction, the subtract instruction, the compare instruction, and also all the other flags that are affected by these instructions. So we're going to go back and talk a little bit about the gates, okay? How to treat the result of an operation and the meaning of these different flags. So let's go ahead and take a look at Find It 1, which is the homework assignment that's due today, a few minutes ago. All right, so I'm gonna do it in the temp folder. All right. Now, if I were to do the homework assignment the way that you're supposed to do it, I'm gonna do it like the way you're supposed to do it. So I will tar the file, into my home folder, and it's called findit1.tar.gz. Go into the subfolder. And take a look at the file. All right, so I'm pretty sure this is familiar to most of you by now. Last time I checked, 47 out of 63 people turned in the homework assignment, so I'm not quite sure whether those remaining 16 actually turned it in or not. But let's go ahead and take a look at the homework assignment. The only part that I think you cannot do it by hand is the conversion of the decimal number into hexadecimal. I mean, you can, but it's really a lot of trouble to do that. So that's the only part that you might find, having a calculator would be helpful. So let's go ahead and do that part first. Okay, so we'll do the conversion of the decimal number into hexadecimal number. Okay. There are several ways to do it. We can go to, the first of all, one tool that can do it is GDB itself. Okay. In other words, if I just go into GDB, I can use it I can abuse GDB as a calculator. Okay, because I can just print stuff, right? So one way to do it is to use GDB without running any program and just say print/x, because that will print a number in hexadecimal. So now I just need to go back here, look at this number, select the whole thing, and then we say copy, switch to the other screen, and paste it. All right. And here we have our decimal number converted into hexadecimal. The reason why I want to convert it into hexadecimal is hexadecimal is very nice because it clearly states the byte boundary. Okay, because every 2 hexadecimal digit is 1 byte. So this way, it's very easy for me to tell how it should be organized as individual bytes. Are there any questions about this part? If there are no questions, so what we'll do next is we'll do everything else kind of quote unquote dry. In other words, we are going to copy this number back into the editor. So this way, I have only one place to look at everything. All right, so we have the code here, and I'll just paste it back into this editor here, and now I can do everything else without using GDB at all. Okay, so the objective is to do it by hand without using GDB, because that way we have a better understanding of the organization of bytes in memory. Right. So we want to find out, exactly how the bytes are organized, and instead of doing this, I'm gonna use a comment line here. And remember, you can do the same thing in your program. Adding more lines of comment is actually okay. I mean that it's not modifying the program itself. So the first thing I would do is to look at every single allocation that I have done here, and then express all the bytes as individual bytes. with this dot word, let me turn on the line number so I can refer to the exact line number when we talk about the program. I'm not sure whether you can see or not. The line number is kind of faint. Is that okay? Can everybody see the line number? Sort of.
Yeah.
Okay. So we'll start with the construct on line 5. The dot word construct is actually technically called a directive. Okay, it is not a command. It is not an instruction. It's called a directive. A directive is an instruction intended for the assembler itself. It is not going to generate actual instructions as the output of the program. Okay, it's telling the assembler, I want to reserve enough space for a word, which is 16-bit, and I also want to initialize those 2 bytes to represent 0xABBA. Okay, and because the Intel architecture is a little endian processor, that means the least significant byte has the lower address. Now at this point, I'm not going to use 0x all the time, just to save space. So BA is implicitly a hexadecimal number as a byte. So BA is the first byte, and then AB is the second byte. Now we move on to the next line, on line 6. We have a single byte with the content of AA in hexadecimal. And then we move on to line 8. Line 8 is a .int. A .int is a 32-bit construct, so I need to now read this thing, but I have to read it from least significant byte to most significant byte.
BB, AA.
So it will be BB, AA, BA, and AB again.
Mm-hmm.
And then after that, we have the dot byte. There are 4 individual dot bytes here. And that I can just read it the way it is specified, because on the same line, we read from left to right. Whatever is on the left is the byte that has a lower address. So now I have every single byte spelled out on line 3 as a line of comment. The next question now is, well, what about the labels? Now let me ask you one question. If I look at L1, is it a label of the dot word, or is it a label of the least significant byte of the dot word? Is there a difference between that description? Well, there's a slight difference. Okay, there's a slight difference. The first sentence, of L1 being the address of the dot word, kind of imply that the word itself, the 16-bit, is one chunk. I cannot address individual parts of that word. The second sentence, which said L1 is the address of the least significant byte of the dot word, specifically said the dot word can be separated into individual bytes, and the address label only applies to the least significant byte. So that would be the way I would describe it, because the i386 architecture is byte addressable, not word addressable. So each address corresponds to the location of a single byte and not of a word. So if I want to document that, then L1 is going to be here. In other words, L1 is the exact address of the byte with the content of BA in hexadecimal. And using this particular notation, where should I put L2? The BB, yep. L2 would be here, and L3 would be the other BB. That's right. Okay. So this way, I know the relative positions of the labels. In assembly language programming, in this particular case, L2 is really exactly the same as L1 plus 3. And then L3 is really the same thing as L1 plus 7. Are there any questions about what I just said? Plus 6, sorry. L3 is really L1 plus 6. Yeah, because it is 6 bytes from where L1 is located. Okay. So I do want to point out all these things. The boundary between dot word, dot byte, dot in, and a dot byte again is non-existent. There's no boundary whatsoever. Yep.
Why is it plus 6 instead of plus 7?
Is it plus 7? Yeah, it is plus 7. Sorry, I take it back. This is plus 7 because there are 7 bytes in between. Yep. Plus 6 would be the last byte right before L3. So it is plus 7. Right. So are there any questions at this point about the memory layout? Now, at this point, if I were to do the homework assignment, I would use GDB and verify that this is actually how memory is organized. which command do you think I should use in GDB? I'm not going to do it, but in case you want to do it, which command do we use in GDB to verify that this is actually how memory is organized?
X.
The X command, examine. Yep, exactly. All right. So now that we have the memory layout in memory layout, we need to find the pattern that will give us the result that we want. We want EAX to contain this particular pattern here. So what is going to be my search criteria? In other words, if you look at line 14 and line 15, which one should I use to give me a clue of where I should be copying from? I should worry about line 14 first, right? Because line 14 is the only one that can set bit 16 to bit 31 of EAX. Whereas line 15 is going to overwrite bit 0 to bit 15 of EAX anyway, so I'm not going to be too worried about those least significant 16-bit at this time. I just need to set the most significant 16-bit of the 32-bit register first. Okay. The most significant 32-bit of the register is going to have the content of AABB. Okay? But when you look at the organization in memory, we are actually looking for the organization of BBAA, because BB is the less significant byte, and AA is the more significant byte. The least significant byte has a lower address. There are multiple solutions in this case, because you can see that. Okay, let me do this line here.
I got L1 plus 1.
Okay, so we can use this one. We can use this AABB over here. Well, okay. Let me just locate the bytes that I want to copy first, and then I'll talk about why it is that by itself is not the answer. Okay. So these two bytes will meet the requirement of having AA first and then BB. Oops. Sorry. Take it back the other way around. So BB first, and then we have AA here. And then it is also over here. So once again, we have BB and then AA here. The next question now is, what am I going to use on line 15? Well, line 15 because I shifted the line at this point, but at this point on line 15, on the move L instruction, where should I copy from in order for BBAA to become the most significant 16-bit and not the least significant 16-bit of EAX? If I choose to use L2, that's not going to work. Because if I use L2 on line 15 at this point and do a move long L2 to EAX, it's going to copy BBAA to become the least significant 16-bit of the 32-bit register. And it will end up using BAAB as the most significant 16-bit of the register, which is not what we want. So what we need to do is to look back 2 bytes to find out where should we start copying. And in this case, there are 2 solutions. With the first instruction, we can start copying from this location, which is L1 plus 1. So I'll just go ahead and indicate this as my first potential starting point. But I can also use L2 plus 2, which is over here, as the underscore of the move L instruction. In other words, there's not a single unique solution. I can use either one. L1 plus 1 is one solution. L2 plus 2 is one solution. L2 minus 2 is also a solution, because it is really naming the same location using a different reference point. Yep, go ahead.
So with L1 plus 1, you're taking AABB from L2 and putting into the most significant, or into the most significant?
Yes, BBAA will go into the most significant portion.
AABB, right?
It will go in as AABB because when we read a number, we read the most significant part first. But when I look at the content, we are listing from left to right, from the low address to the high address.
So then L1 plus 1 will be AABB, AABA.
L1 plus, if I load it from L1, it will become AABB, AAAB, which is actually the solution inside.
Yeah.
But since you have the second instruction, you still have to figure out what to do with the second instruction. In this case, to preserve the 16-bit that is already there.
It's same.
That's a trivial solution, right?
It's the same.
It's the same, exactly. Okay, so just to get here, to give you the solution here, there are two distinct solutions. One is L1 plus 1, and the other one is L2 plus 2. Now, if you want to refer to L1 plus 1 as L2 minus 2, that's okay, but I would not consider that a distinct solution. It's just an alias of a particular address that we also call L1 plus 1. So are there any questions about the move long instruction? Are there any questions about the move long instruction? Questions about that?
And so no matter where you start from, it'll take the next 4 blocks.
That is correct. In other words, you're absolutely right. The operand of the move long instruction specifies the address of the first byte that you're copying. Because it's a move long instruction, it's going to copy 4 bytes. It starts with the location that you indicate, and then it will also copy the 3 other bytes after that so that it is copying exactly 32. Okay. Now, it doesn't understand the boundary between a dot word, a dot byte, dot in, and so on. Those boundaries are completely artificial in our head. As far as the assembler is concerned, as far as the instructions are concerned, you just give it the location of the first byte, and it will say, okay, how many bytes am I supposed to copy? 4, because it's a move long, and then it will use the little end-in method to move the byte from the lowest address into the least significant byte and use that order to load all 4 bytes into the destination. Are we doing okay so far? Sorry? Say again. For the assignment? You have to specify, the operand for both. So even though the first instruction can accomplish the entire thing already, you still have to specify the operand of the second instruction.
Like, I'm talking about like, okay, I will say
You only have to specify one of the two.
yeah, L1 plus 1 and plus,
Yes.
or L2 plus 0.
Yeah.
0. That's fine.
Yep. One of the two is fine. All right, so let's take a look at the second instruction. With the second instruction, okay, if you pick L1 plus 1 for the first instruction, you just have to use L1 plus 1 again for the second instruction, because we just want to move the same 2 bytes into the least significant 16-bit of the register. So that's fine. Okay, can I help you guys? Are there any questions? Do you guys have any questions? Okay. So we can use L1 plus 1 here. The least significant 16-bit has a pattern of AA, AB when we read it from most significant digit to least significant digit. When we look at this as a byte sequence, it would be AB, which is the least significant byte, and then AA. So if you're looking for ABAA, ABAA, L1 plus 1 is 1, and then AA, that's the only one. So for the second instruction, there's only one unique solution, whereas for the first instruction, there are 2 possible solutions. That's it. That's how this particular assignment works out. The purpose of the first homework assignment of this one, this is not the first homework assignment. This is actually our 3rd homework assignment already. But the purpose of this particular assignment is to make you guys think about how bytes are actually organized. Okay. And also to break the habit of a high-level programming language programmer that basically thinks, oh, .int, okay, I cannot cross that boundary. I cannot cross the boundary and copy from, somewhere within the .in and somewhere out of the .in. There's no such thing as a boundary. There's no such thing as a type when assembly language instructions execute. All right? Are there any other questions? And also part of the objective is for you guys to get used to GDB, because I'm hoping that most of you ran GDB enough to at least understand the most useful instructions: print, X, L, run, breakpoint, single step. Okay, so those are the instructions that you need to understand because we'll be using those commands in GDB for the entire semester or for the rest of this semester. Are there any questions about the GDB commands? No questions? Did anyone try to right click in GDB and see if it pops up a menu so you can say breakpoint here? No? Well, you might be able to do that if you use, there are GUIs that sit on top of GDB. I cannot remember the names of those things. I think one is called DDD. It's one of the GUIs on top of the GDB. Let me just double check. Now I need to find out. Yep, Data Display Debugger is it's basically a graphical overlay on top of GDB. So this is a graphical front end for command line debuggers such as GDB, DBX, and so on. So if I give you a screenshot, some of you will say, I want to install that because it's all GUI based.
Is it worth trying out?
No.
No.
I don't think it is, because these GUIs, ultimately, if you use the virtual machine, you have to install the entire external system first. It's not worth that trouble. I have used GDB, just fine, for all of my own personal debugging. In fact, for some of my programming, the only tool that I had for debugging purposes was 2 LEDs. On the circuit board, there were 2 LEDs on the circuit board, and I can only tell, did I get to that point of that program? Yes, it lit up. No, I didn't quite get there. That was the only tool for debugging. Okay, I was writing a real-time kernel, and as a real-time kernel, I cannot use high-level programming languages because I have to go below, the C language to access the registers and whatnot. So I was writing that thing. I could not use, GDB because there's nothing to communicate with the chip. I was too cheap to buy a in-circuit emulator. So I only got a programmer that can put a program onto the chip and let it run. But I cannot stop the execution of the program at any point and inspect variables or registers or anything like that. So my only tool was the 2 LEDs that I have, on the circuit board, and that was it. But I have to tell you, this is actually considerably easier than what I had to do in my previous job. Now with the AVR chip that I was using, at least it could do in-system programming. In-system programming means you have a chip that can store a program, but in order to program that thing, you just have to plug in like a USB dongle to that board and then run a specialized program, and you can reprogram the chip without having to desolder anything or take the chip off or anything like that. Okay, so I can just sit on my desk and keep doing it like that. Keep doing it by changing the program, observe the LED, analyze the program, change some more, and so on. In my previous job, the flash technology was just emerging at the time. Okay, and I had to use EPROMs, EPROMs, in order to store the program onto those particular boards. EPROMs stand for erasable, programmable, read-only memory, which is kind of contradictory if you just kind of read the name itself, right? Erasable, programmable, read-only memory, okay? And the way you erase it is not like, oh, run the command, and it's erased, or right-click somewhere, and it will get erased. You have to remove the chip physically from the circuit board, put it onto a tray, stick it into what we call a UV eraser, and the UV, the ultraviolet light, would actually do the erasing. It takes about 15 minutes of exposure to erase the content on these chips. After it is erased, you put it onto what we call a EEPROM programmer. Okay, and those things, back in those days, connect through the parallel port to a PC. And then you reprogram the chip, and then you put the chip back onto the circuit board, you power up the board, and you observe whether the LED is lit up or not. And then you repeat the whole cycle. That was a little bit more painful than what you guys have to go through with GDB.
Quite more painful.
Sorry?
It's quite more painful.
Well, it is still not as painful as what people had to do in the mainframe days, because in the mainframe days, they have to write a program on punch cards, and then you submit the job, okay, and they will run your job, overnight, within 24 hours or so, and then the next day they give you a big pile of paper, which is the output of your program. And then if you have to change your program, you might have to repunch the entire program. I think you can type something, and then there are later on there were machines that can actually do the punching for you. But nonetheless, your program is one big huge stack of punch cards.
But how is it become stuff is this stack? But you should punch a little bit stuff.
Say again?
If you're only punching a little bit stuff, then why is it a huge stack?
Because one card is only going to specify a very small instruction, maybe one statement, maybe one line. Because it's not binary. Okay, on a punch card, each column corresponds to one column on that line, and then on that column you have to select. Okay, is it an A, B, C, D, and so on? It's not in binary, so that's why it is very. If you look at the holes, there are very few holes on each punch card, so the information density is very low. That's why you did a big, huge pile to represent anything that's useful. So anyway, getting back to the homework assignment. So if there are no questions about this particular homework assignment, we'll go ahead and take a look at the next one, which is Find It 2. And I promise Find It 2 is the last one, the last Find It series homework assignment. And here's Find It 2, same thing, download the file first. I'm just going to put it into my temp folder. And you can save that one. And this time I'll take a look at the other one, tar ccf xzvf/temp/findit2.tar.gz. All right, so here's the other program. So instead of using AB, I'm just using zeros and ones this time. Okay, but it's just 2 digits, right? And then the nature of the program is about the same. By the time execution gets to the label test here, ECX this time should have the content of 0x. See, this time I'm doing you a favor. You do not need to use a calculator to convert from decimal to hexadecimal. It's already in hexadecimal. So you should be able to do this whole thing without using GDB at all. You should be able to do it dry. Okay, and then without using GDB, turn the file back into me. Okay, so these are all zeros and ones, but the instructions are different. The 2 underscores are here. Let me turn on the line numbers so that you can see where what you can change. On line 11, you can specify a direct operand because the underscore is not preceded by a $sign. It's not preceded by a percent. It is not in parentheses. That makes it a direct operand. Okay, so that underscore has to be a direct operand. On line 12, you can specify the underscore, but you cannot change the $sign. So that one has to be a immediate operand. Okay, and then the other 2 instructions on line 13 and 14, those are the ones that will actually move something or copy something into ECX. So you have to figure out what needs to be in ECX, look through the memory content and try to find the byte pattern that you need, and then go back and try to figure out, okay, I know what I need from memory, but how do I make it happen? Now the trickiest line of this entire thing is line 5. Okay, so you will have to figure out what line 5 is going to do. L2:.int L2. Okay, I'll give you a few clues, okay, but you have to put the whole thing together. L2: is the definition of a label. In other words, at that point of the program, the assembler says, oh, okay, so you want to put a label here as a bookmark for this particular memory location, and call it L2. Fine, okay? But when you look at L2 from a different perspective, it is nothing more than a 32-bit integer. Okay? Every label is really just a 32-bit integer. Or this is one way you can look at it. underscore start is no different. It is just a symbolic name of a 32-bit integer. Okay? So if L2 is really just a 32-bit integer, why can't I initialize, allocate 4 bytes and initialize those 4 bytes to be that particular number? Nothing says that I cannot do it, right? So you have to keep that in mind.
But we don't know that number.
Sorry?
We don't know that number.
We don't know
That number.
that number.
Yeah.
Well, that number depends on the kernel, okay, and it depends on a lot of factors.
Yeah.
So you cannot really you cannot predict what that number is going to be.
Okay.
Okay. Are there any questions about this? Okay, hold on. He raised his hand.
So even though you use 1s and 0s, those are still hexadecimal, right?
They
So-
are, yes, they are all preceded with 0x, 0x, that means they're all hexadecimal
Happen to use
numbers.
1 hexadecimal. Okay.
Yeah, they're not binary.
That's.
Well, you just,
Got
you
it.
just spoiled the part of the fun because I was hoping that someone would look at this and go, oh, binary numbers.
Not that.
That's okay.
Yeah, when I first saw it,
I'm going to say it again, the pattern that you have to look for is 10010100 in hexadecimal. I think that should answer your question. That should answer your question. Okay. So are there any questions about the nature of the homework assignment? I would do about the same thing as what I did earlier. Okay, I would try to spell out, the byte patterns of the entire thing, except for the 4 bytes at L2, the .int L2. You just put question marks, with those 4 bytes because you really don't know what would be the content of those 4 bytes. Okay, but there's a reason why, I have those 4 bytes. There's a significance of the .int L2 over here. So you have to kind of figure out, how your program is going to utilize those 4 bytes. And yeah, go ahead.
So you don't want us to change anything on lines 13 and 14?
Line 13 and 14. No, you cannot change anything on line 13 and 14. You can only replace the underscores with something, but you cannot change the operand type either. So the first one on line 11 has to stay as a direct operand. The second one on line 12 has to remain as an immediate operand. But you get to specify, what the direct operand, specifies, and you also get to specify what the immediate operand can specify. Okay. Are there any other questions? Yep.
Is that a -4 and an L3 minus 4 on 13 and 14?
Yeah, it is L3 minus 4 on line 14.
And 13 is -4?
And on line 13, it is a -4. Yep.
So when we have formula, it's minus. It's not plus, but minus. And the formula is minus. Yeah.
It is just a minus.
Yeah.
Yep.
Because it's like a sum.
Yep. Exactly.
In this case, we have minus.
Yep. Yep. This is just a -4 here. Yep. All right. So are there any questions about this homework assignment? Okay, another clue. Okay, you have to read up on the addressing nodes. So you have to identify each and every single one of these addressing nodes and then find out how the effective address is calculated. That whole business about the displacement, base register, index register, and scale is going to come in handy in this case. But there are certain things that are already fixed. Okay, if you look at line 14, the displacement is fixed already. And you only get to play with EDX, which is a base register. Okay? If you look at line 13, the displacement of -4 is already determined. The scale is already determined to be 2, and the 2 registers are also kind of determined because you know which 2 registers are going to be used in this case. So you kind of have to think about this and find out which one gives you the most constraint. Okay, find out which one gives you the most constraint first. Work it out and say, okay, this can be this, can be that, can also be that, and then use that to try to work out the other instructions. Okay. Are there any questions about this particular assignments. Yep.
For the data.
For the dot data.
So, for example, Word, one has a 2-digit, second has 3 digits, one, for example, have leading 0, but that word doesn't have leading.
There can be implicit leading zeros, yes.
Implicit.
Yep. I was hoping that no one would ask that question and I can just quietly stay stealthy and not mention anything about it.
Yeah.
But that's okay, since you mentioned it, it's already being recorded. So for those of you who just said, what did you say? It's already recorded.
Asking more.
Yes, on line 4. Okay, so let me just make it fair so that everybody can hear that. On line 4 and other lines potentially, I'm not going to say which other line, leading zeros are, some of those leading zeros are not spelled out. It's just like, when you try to pay someone $5 and then you want to say, okay, this is worth $5, you don't say 0000005, right? You just say 5. All the leading zeros, you usually don't spell it out. So it's the same thing here. So you just kind of keep that in mind when you try to work out the patterns.
0101.
Okay? So are there any other questions about this homework assignment? It might take you a little bit of time to kind of work it out, but I think it is worth it. Okay. I really like these homework assignments where there are only 2 lines that you have to do something about, and and it will take you a week to do it. I hate homework assignments where you have to write like a 500-line, visual basic program, based on the business logic that is described, as a 5-page document. That type of thing, bugs me because it's tedious. This is not tedious. 2 lines. Come on, 2 lines. And even the instruction and the addressing modes are all determined already. All right. So that's your new homework assignment. You have 1 week to finish this homework assignment. I suggest that you try to do it as soon as possible. Start on it as soon as possible so that on next Tuesday, if you have any questions, I can try to address and answer those questions. It would not be a good idea to wait until next Tuesday to start on it. Except if you're super genius, then it's okay. This is not an open challenge, by the way. I'm not saying that, I will wait until the last moment and see if I am a super genius or not. All right, so we are now officially moving on to the next topic. We are now officially moving on to topic 3, where we will talk about the addition instructions, addition, subtraction, and all the other ones. Okay? All right, are we ready to move on? Okay, let's go. Okay, so for anything that you guys want to talk about regarding this stuff here, let's do it after the class. Okay, so now let's move on because I don't want you guys to talk about something that is in the past so that you miss the future. That's not a good trade. Okay, so let's focus on this new stuff here because there's really quite a bit of new things that we have to worry about. Okay, and I'm going to open up multiple links here just so that I can find out which one is the more recent one. Subtracting in assembly language, we'll talk about subtraction later. Let's deal with addition first. Okay, this is older, but it's still good stuff. Okay, it is still useful. Okay, this is the stuff that we have talked about already. Binary addition, binary subtraction. We talked about all that stuff already. But what we'll do this time is we'll talk about the instructions that will do the binary addition and the binary subtraction. So let me go back. Okay, let's open it like this. Okay, the first thing we want to do is to talk about negation and signed versus unsigned interpretation. This is the first thing we have to go over. And why is it opening up like this? There we go. All right, so the first question is, what is, the interpretation? What is signed and what is unsigned interpretation? Okay, so that's the first thing we have to deal with. When you look at a binary number, what do you think a binary number consists of? It's a base 2 number, so you can only have zeros and ones. Okay, very good. When you look at the representation of a binary number in terms of transistors, gates, and stuff like that, okay, what do you think would be, how do we describe the state of a gate or the state of an address line or data line for zeros and ones?
0 is off, 1 is on.
Okay, or it can be the other way around. Okay, but a transistor can either be on or off, right? A gate can either be outputting high or outputting low. Good. Then how do we represent negative numbers? Is there a negative transistor? No, there's no negative transistor. Okay, so that means, sorry? The direction is opposite? No. No, we have to represent both positive numbers and negative numbers only using zeros and ones. This is not a typical problem that you have to deal with in normal arithmetic. But when you try to represent numbers in the computer, then you have that problem. Because computers, almost all digital computers that we use today are all binary computers. In other words, each transistor, each memory location can only represent either a 0 or 1, a high or a low, assertion or negation. So now we have to look at, let's look at this number here, okay? 0, 1, 1, 0 as a base 2 number. What is it actually representing? 6. Well, you can look at it as 6, right? Okay. What about this one here? 1, 1, 1, 0 in base 2. 14, okay, 14 is correct. Great, what about this one? 0, 0, 1, 0 in base 2, that's an easy one. 2, right? Well, okay. How do we represent negative 2?
Switch.
Now, I wish we could do something like this, right? It's just a negation of 0, 0, 1, 0 in base 2. But we can't, okay? There's no bit to represent the negation symbol, okay? So we can't do it that way. Now, some people would say, well, can't we allocate one of the bits, particularly the most significant bit, as what we call a sign bit, and say, if this is a 1, then it is representing a negative value. The rest of it is just representing the magnitude to the negative side. We can do it that way, but it's not convenient. Okay, it's not convenient for at least 2 reasons. The first reason why this is not convenient to represent negative 2 is, what about this pattern here? What is it actually representing? It's representing 0 again. Because 0 is just 0. It doesn't matter which way you look at the number line. I'm going in this direction, 0 steps. I'm still here. I'm going in this direction, 0 steps. I'm still here. So 0 now has 2 representations, which is not useful, right? Because the value represented by 1, 0, 0, 0 in base 2 is the same as the value represented by 0, 0, 0, 0 in base 2, which is really just our usual 0.
It's like
Okay.
0 and minus 0.
It's minus 0, okay? It's the same thing as 0. It is not meaningless. It is just a duplicate of the normal way of representing 0. Okay, so this is the first reason. The second reason has to do with we can no longer just use our usual add logic to perform addition. Because now we have to look at this sign bit here, the most significant bit, and then we have to do things in a different way depending on whether it is a negative number or negative value or positive value. So this is not very handy. Okay, you can do it this way, but you will end up using a lot more logic gates in the processor in order to represent negative numbers using this method. Okay, so that's why we don't use this method to represent negative numbers. All right, so you erase that. So what do we use to represent negative values? Well, this is what we do. 1, 1, 1, 0 can represent negative 2. Okay, so at this point, what I'll do is I'm going to use a mouse pad so that we can actually capture all that stuff in the video. Yep.
But then, if you're giving the negative 2 to like 1, 1, 1, 0, If you look in the binary right now, isn't it becomes like 2 plus 4 plus that? Isn't it 14?
It is also 14.
Now, how do we know when it's 14, when is it negative 2?
You do not. You do not. Now this. You asked a very good question. If we use 1110 to represent negative 2, then what about 14? Well, the meaning or how you interpret a number is different from C and C++ or any high-level programming language. When you use a high-level programming language, the type of the variable tells you it is a signed number or it is an unsigned number. It tells you how you're supposed to interpret the bits. When you deal with assembly language programming, the move instruction doesn't care. Okay? The add instruction does not care either. In other words, whether your numbers are signed or unsigned, we still use the same add instruction. We still use the same subtract instruction. We still use the same compare instruction. So when does it actually make a difference? Is the flags that they set after the operation. Okay? So that's a very good question because I cannot answer that particular question today, but later on we can answer that question. But I can only tell you that bits are not, they don't have really a negative sign associated with it. Okay, there was a hand. Yep, go ahead.
So is the range between 7 to -7 or 8 to -7?
Say again?
Is the range for that system 7 to -7 or 8?
That is also a good question. Okay, if I only use 4 bits, okay? Now this one way to look at this is really useful. I never really drew that and put it in my notes, so you might want to write it down here. Is to look at everything as a wheel, okay? Now most of you, having taken a math class, you under the concept of a number line, right? A number line, basically just stretches out to infinity on one side and also stretches out to infinity on the other side, and it is just a line. But in computer science, when we talk about number representation, we use a wheel or a disk to represent the numbers, okay? That's because with 4 bits, how many combinations of zeros and ones can I have with only 4 binary digits? 2 to the power of 16, right? Because the first digit has 2 combinations, or zeros and ones. The next digit, which is independent to the first one, has 2 choices. The next one has 2 choices. The next one has 2 choices. So we're dealing with 2 to the power of 4, which is 16 unique combinations. And since 2 to the power 16 is small enough as a number, I can just go ahead and write it in the number disk. So the first one is just 0, 0, 0, 0. The next one, okay, I can. And we have. By the way, this is how I cut a pizza too.
Using binary?
No, it always divides into a 2 to the a power of 2 slices.
2 to the 4, 16 pieces, 3 slices.
And I also cut a pizza into 16 slices always.
Why 16? That's good.
We use 4 beats.
That's too much to read.
Okay, next one is what? 0, 1, 0, 0, because I'm just adding 1 to each one, right? The next one is 0, 1, 0, 1.
0, 1, 1, 0. 0, 1, 1.
Okay. Is everybody satisfied that this enumerates all 16 possibilities when you only have 4 bits? Okay. Good. Okay. So the first thing is the easier one. Okay. If you look at these bit patterns in a quote-unquote unsigned interpretation, what values are they actually representing in base 10? Well, that's easy. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and 15. 15 is 2 to the power of 4 minus 1. Makes sense. Okay? But great, but what about negative numbers or values on the negative side that we want to represent? Yep.
Well, like using the base 10 interpretation, anything greater than 7 is okay.
correct. Okay? So the way we represent negative numbers is to start with a 0. Okay? Now, let's not worry about the negative numbers. Let's just look at 5 and 4. Okay? 4 is in the counterclockwise direction of 5. Does that make any sense? So it seems like clockwise is going negative, clockwise is going positive. Is that okay so far? That trend is okay. So when you look at 0, what if we go to the negative side of 0? Well, it will be this particular bit pattern. But we can associate this bit pattern 1, 1, 1, 1 with the value of -1. -2, -3, -4, -5, -6, -7, and -8. Okay? This is how the number wheel works. Okay? Yep.
That's because 0 is technically counted as a non-negative.
0 is counted as non-negative.
Right.
So this way we have exactly 8 non-negative values from 0 to 7, and exactly 8 negative values from -1 to -8. So the number of negative numbers matches the number of non-negative numbers. So what is really nice about this representation is if you want to do calculations like addition or subtraction, you can, it works out just fine.
It's like negation.
Well, that's one way to look at it, but the other way to look at it is, you just twist the disk one way or the other way with a certain number of steps. Okay? In other words, if you imagine that, there's a little pointer here that does not move, and you rotate the disk in order to do calculations, that means if you want to add 3 to a number, you just rotate it counterclockwise 3 times. If you want to subtract 4 from a number, you rotate it clockwise 4 times. Okay? And it works for both the positive number as well as the negative numbers, as long as you do not cross this line. Okay? Because when you cross that line, then you basically are running out of representable values for 4 bits. But as long as you don't cross this line, as long as this line is not crossed by the marker, the calculations will work out just fine. Is that okay so far? Okay, so this is why we represent numbers using this particular scheme. But how do we know that, okay, if I give you a particular negative value, how do I know the binary representation of that negative value? That is what we need to talk about next. This whole thing is called 2's complement. And using just a regular text editor, I'm going to use C2 to represent 2's complement. So what I'll do is let me change the font size first. We'll increase the font size to 17, so this way it's easier for everybody to see it. Okay, so the C2 is 2's complement. And you basically look at a particular bit pattern. We'll call X a particular bit pattern. C2 is the 1's complement of the same bit pattern plus 1. That's it. And now we have to explain what is 1's complement. C1 is 1's complement. And 1's complement is just flipping the bits. Flipping 0 to 1, 1 to 0. Okay? Is that part okay so far? Does everybody understand what is 1's complement? There is a C operator to perform 1's complement. It's also called bitwise NOT. Does anyone know what that operator is? Say it again? Exclamation point? XOR? You can use XOR to accomplish that, but it's not. If you want to name a unary operator, which one would that be? In other words, it's an operator that has only one side. Is the tilde symbol. The tilde symbol in C is bitwise NOT. Okay? So I'm just going to put it here. This is, okay, C1 of X is in C, it is the tilde of X. Did you guys talk about this operator in C and C++? Sorry? Yeah. Okay. It's not usually used because a lot of times, in C and C++, you don't really need to manipulate individual bits. this is really useful in this class. Okay, so what we'll do is we'll go through a few examples just so that we know what is 2's complement and what is 1's complement. Okay, so let me just ask you this question: what is the 1's complement of? Let's start with something simple. Okay, and this is really just dealing with a chart. Because 0x00 as an integer has a default type of an integer, and the width of an integer depends on the architecture. So depending on whether you're using a 64-bit architecture, a 32-bit architecture, or a 16-bit architecture, just naming 0 can be 8-bit, 16-bit, 32-bit, or 64-bit. By casting it into a chart, I am now saying specifically this is an 8-bit representation of 0. Okay? So what is the 1's complement of the 8-bit representation of 0? First of all, what is the 8-bit representation of 0? 8 zeros, very good. Okay, 0, 0, 0, 0, 0, 0, 0, 0. Is that okay? Okay. So what happens when I flip all the bits, zeros into ones and ones into zeros? It becomes all ones, right? And all ones, and if I have 1, 1, 1, 1, 1, 1, 1, 1 as a binary number, what do you think is the hexadecimal representation of that binary number? FF. Okay. Yep, that is absolutely correct. So using the C operator comparison, this comparison will be successful because the bitwise negation of 0x00 is all ones, 8 ones in this case. Am I doing okay so far? Is that okay? Okay. And using our new notation, it is basically saying C1, the 1's complement of 0, 0, 0, 0, 0, 0, 0, 0 is just 1, 1, 1, 1, 1, 1, 1, 1 in base 2. Any questions about this step? Let me give you a different case, okay? So what about this one? We'll say 4b in hexadecimal. What is the bitwise knot of 4? There's a quick way to do it. There's a quick way to do it. What you do is you use you subtract 4 from f in hexadecimal. F is representing 15, so it's 15 minus 4, which is 11. 11 is represented by the hexadecimal digit of b. Okay, so it becomes b. And what about the other one? Oh, this is trivial. B4, exactly. Because the negation of b is 4.
Oh, so
Because the negation of the negation is itself.
Oh, so they both are subtracted from FF? Huh? They both are subtracted from FF?
Yeah. Yeah, subtracting something from f from 1, 1, 1, 1, 1, 1 is doing 1's complement. It's doing the same thing. Now, does it make sense? Does that make sense? You look at 1, 1, 1, 1. You subtract 0, 1, 0, 0, which is 4 in this case. What do you get? 1 minus 0 is 1. 1 minus 0 is 1. 1 minus 1 is 0. 1 minus 1 is 1. So this operation is really doing exactly the same thing as doing the 1's complement of 0, 1, 0, 0. Okay. Let's try. Okay, now that we know what is 1's complement, let's work with 2's complement. Okay, so we want to find the 2's complement of, let's say 2. Okay, we want to represent 2 as a 4-bit binary number, which we already know is 0, 0, 1, 0. This guy over here. Okay, so we want to take the 2's complement of 0, 0, 1, 0 because the 2's complement of 0, 0, 1, 0 is going to represent -2. In other words, when you see C2, it is the same thing as taking the negation in arithmetic of a number. Okay, so I will spell this out. This is basically the 1's complement of 0, 0, 1, 0 plus 1. 1's complement is just flipping the bits, so it becomes 1, 1, 0, 1 plus 1, and 1, 1, 1, 1, 0, 1101 plus 1 is 1110. Is that part okay? You know, the 3 lines of the derivation? The first line breaks up 2's complement into 1's complement and an addition. The second line is just carrying out the 1's complement, which flips all the bit zeros into 1s and 1s into zeros. And then the last line is really just finishing the addition operation. Say again? Because it's in 1's complement. 1's complement is bitwise not, which is the tilde operator. Okay? All right. Let's see whether this works out or not. Now, how do I check whether this is a proper representation of -2? If I add this number to 2, what should be the result of that? If I add -2 to 2, I should get 0, right? So let's go ahead and see if that works out. And some of you are very skeptical because it cannot possibly be 0, right?
Yeah, prove it.
Because, yeah, prove it. 1110 plus 0010, and I'm going to write here, this is the representation of -2, and this is the representation of 2. So we'll find out whether that kind of adds up to 0. And some of you go like, there's no way it can add up to 0. Okay, well, let's take a look. Okay. And there's no carry from the previous digit because this is the least significant bit already. 0 plus 0 is 0. 0 plus 0 is also 0. And neither addition or neither of the half adding yields a carry. So the carry to this digit is going to be a 0. 1 plus 1 is 0. Whoops. With a carry of 1. 0 plus 0 is 0. Are we doing okay so far? Okay. 1 plus 0 is 1. 1 plus 1 is 0 with a carry of 1. 1 plus 0 is 1. 1 plus 1 is a 0. Attack, you're wrong. We got a 1 over here. Well, but since I'm only using a 4-bit representation, I ignore that last carry. It's truncated. So I am actually right. Okay, 1110 plus 0010 is actually 0000 with a carry. Okay, so that carry is going to be important later on. Okay, but since I'm only using 4 bits here as a representation limitation, there's nowhere to represent that extra carry. Is that making any sense? Because I need everything to fit within this wheel or this disk here, so I cannot, there's no place to represent the extra carry, and as a result, that extra carry is not a part of the number. In other words, when I say addition, it is actually addition with a condition. Okay, we're actually performing. What is the name of this type of math? Modulo. Okay, it's called modulo arithmetic, where you have only a certain limited range of numbers that you can actually represent. It's modulo addition. Am I still doing okay so far with the addition? Why I kind of cheated so that -2 plus 2 is actually 0 in this case. Okay. Well, maybe that's just a fluke. Maybe this won't work with other numbers. Okay. So we'll try this out with some other numbers and see if it works out or not. In other words, we'll try this one. Okay. 1110, which according to TAC is representing -2, and this time we'll add it to 0111, which is representing 7. Okay, and we want to see whether the result is actually 5, because it should be 5, right? -2 plus 7 should be 5. So we'll go ahead and carry out our binary addition. And by the way, did I do anything special about the addition itself? Did I break any of those rules that we have talked about at the very beginning of the semester?
Just a truncate.
0 plus 0 is still 0. 0 plus 1 is still 1. 1 plus 0 is still 1. 1 plus 1 is the only one that has a carry of 1 but a result of 0. All of those things that we talked about at the very beginning of this semester is still okay. Now that is the nice part, because that means when you use the 2's complement to represent negation, we can use exactly the same hardware for adding or subtracting, and for comparing. Okay? That really is one of the nice things of this type of representation. But let's go ahead and finish this calculation first. 0 plus 1 is 1 with no carry. 1 plus 0 is 1 with no carry. Now, since neither of the half adding is contributing a carry, this carry is going to be a 0. 1 plus 1 is a 0 with a carry. 0 plus 0 is a 0. Okay. 1 plus 1, once again, is a 0 with a carry. 0 plus 1 is 1 right there. 1 plus 0 is 1. 1 plus 1 is a 0 with an extra carry. But once again, the carry, this extra carry, has no place to store. My storage is a 4-bit word, so I cannot really store the extra carry. And as a result, it is just 0, 1, 0, 1, which is representing 5. So it does work out. Yep, go ahead.
So, the way that we figured it out, kind of, I don't know if this is true in every case, just want to clarify it, is that if you treat the most significant number in the binary code as a negative, and then add every other number that is represented by the binary, it should give you the correct negative number.
You don't even need to look at the most significant bit any differently.
Or you just treat it, or you just take the most significant number and subtract all the or if you just take the most significant number and subtract the sum of the rest of the binary code, it gives you, and then it should give you the negative.
Okay, the 2's
So
complement.
like for instance, 1110 14 could be represented by negative 8 plus 6, which is the remainder of the
Right.
binary. I mean, does that always work?
Yes.
Okay.
Yeah. Okay, that's a good question. Okay, and I can expand that a little bit, and basically say what if I'm given a number with the most significant bit being 1? I know it's a negative value, but what is the magnitude of the negative value? I think that would also help address that particular question. There was a hand earlier. Yep.
So, for we just give any random numbers, not if the 0, 1, 1, 1 and 1, 1, 1, 0, they don't complement each other anyway, right? They don't complement, they're just two random numbers, right?
One is representing -2, the other one is representing 7, so they are not related, in any way. Okay, so the next question is, if I just give you a particular bit pattern, let's say 1010 as a bit pattern, if I want to look at this in a sign from a sign perspective, I know it's a negative value because the sign bit, which is the most significant bit, is a 1. But how much is it on the negative side? What is the magnitude to the negative side? Well, I can apply 2's complement again. Remember, the 2's complement applied to a number is equivalent to normal arithmetic, just doing the negation of that number. Is that part okay? The special binary operation called 2's complement is really doing exactly the same thing as the arithmetic negation in normal math. Is that okay? All right, so if that is okay, then we can apply 2's complement to this particular bit pattern, 1010. It breaks down to 1's complement of the same bit pattern plus 1. 1's complement is bitwise not, so we're just flipping the bits 0 to 1, 1 to 0. So this becomes 0, 1, 0, 1 in binary plus 1, and we end up with 0, 1, 1, 0, which is usually what we call 6. Okay, so that means 1010 as a 4-bit number, when you look at it from the sign perspective, is actually representing -6. Is that matching what we have on the number wheel? Yep, it does. Okay. So now we have a way to perform arithmetic negation by only using an addition and also bitwise not. Do you think that the operation of bitwise not can be done by a logic gate?
Yes.
It's called a NOT gate, right? How about addition? How about adding 1 to a number? Can we do that using logic gates? We have done that, right? We have done that, early on in this semester. Okay, addition can be done by full adders, and full adders break down to half adders. Each half adder breaks down to AND gate and NOT gates. AND gate, OR gates, and NOT gates. Okay, so now we have a way to implement arithmetic negation, but only using gate logic. Okay, just logical gates, which is great because now we have a way to implement it in the processor. Are there any questions at this point about what we have just talked about? No questions? Okay. So if there are no questions, then we flip back to the notes here. The next topic is to talk about what is status flags. Okay. This is a very general discussion. The status flags are basically a way to store the result or the characteristics of a result after an add operation or a subtract operation. The 0 flag is set to a 1 if and only if the result is 0 itself. Okay? So if you look at this and you want to represent it using gate logic, how are we going to represent this gate logic here? I'm going to go back to my note here and say the Z flag. Okay, so let's look at the result. Okay, the result is, let's say the result is 4-bit. It is represented by bits W, X, Y, and Z. Okay, W being the most significant bit, W is the most significant bit, Z is the least significant bit. So knowing that W, X, Y, Z are all individual bits, how do I express the 0 flag when the 0 flag should be a 1 if and only if all the bits are zeros? Okay, but I cannot do equal. I cannot check for equivalence. The basic gates are AND or NOT. So how can I utilize AND or NOT in order to define the Z flag?
Or Y, or W or X, or Y or Z negated. So
The whole thing negated.
so
Yep.
Not the whole thing.
You're absolutely right. It is the negation of W or X or Y or Z.
And you have an extra 3 sets for, 3 sets of parentheses, because you can't do, logic 4 gates only have 2 inputs.
Right, but I've just kind of pretended you can. There are actually OR gates that you can have multiple inputs. That's actually a valid assumption. Okay, is that okay? Can everybody see that if any one of the bits W, X, Y, or Z is non-zero, Z is going to be 0 itself. Okay, because if any one of W, X, Y, or Z is a non-zero, then the disjunction is going to be a 1. But if you flip using the NOT on the outside, the 1 turns into a 0. So that means if the result is non-zero, the Z flag is going to be a 0. If the result is actually a 0, where W, X, Y, and Z are all zeros, then the disjunction itself is going to be a 0. But when you put a negation or a NOT gate on top of 0, it becomes a 1. Is that okay? All right. So this is one of the flags, okay? One of the flags that the computer can track when it performs the operation. The carry flag is the extra carry that cannot be represented, okay? So the carry flag, if I go back to my notes here, is really this guy here. Is it a 1 or is it a 0? That's the carry flag. Now the carry flag has significance, especially when we perform subtraction. Okay, when we perform subtraction, the carry flag or the borrow flag in that case has a particular meaning. The next one is called the sign flag or the negative flag, depending on how you look at it. The sign flag is easy. If you're only limited to a 4-bit representation, the sign flag is really just the most significant bit. In this case, it is represented by W. If the sign flag is a 1, the number is representing something that is negative when it is interpreted as a signed number. If the sign flag or the most significant bit is a 0, then it is representing a positive number, a non-negative number. Are we still doing okay so far? Yep.
So in assembly languages, like in this kind of stuff, there's no such thing as an unsigned number?
Okay, that is a very tricky question. Okay, the question was, in assembly language programming, is there not such a thing called unsigned number? Is that your question?
Yeah, I'm doing right now with.
Okay. When you add two numbers, it's the same instruction to add numbers whether they're signed or not. When you subtract, it's the same instruction whether it's signed or not. When you compare, it is still the same instruction whether it is signed or not. So these three instructions, add, subtract, and compare, will change the flags that we are talking about. So the Z flag, the carry flag, which is also the borrow flag, as well as the sign flag, will all be set according to the result by these instructions. Is that okay?
Okay.
But the instruction to utilize these flags is not add, subtract, or compare. It's the conditional branch instructions. So in other words, when you're only doing calculations like addition, subtraction, or even comparison, there's no difference whether you're dealing with signed or unsigned numbers. The only time when it does make a difference is when you need to make a decision and say, is this number less than that number? Then you have to pay attention to whether the number is represented signed or unsigned, because you have to choose a different conditional branch instruction whether it is signed or unsigned. Now, since we are quite, some way of, we're not quite there yet to talk about conditional branches, so I will defer that discussion. But that's a very good question. Okay, that is a very good question, because the answer is the instructions that we have talked about so far has no sign sensitivity whatsoever. Okay. Now we'll just go over the last one. The last flag that we have to talk about is called the overflow flag. Now the overflow flag is really, really kind of strange because it says the sign of the result makes no sense. Okay? It's called the overflow flag because you have just overflown the numbers that can be represented given the number of bits. Okay, what does that mean? Well, exactly, when you exceed the range. Okay, so let's go ahead and try to exceed the range. That's an easy one to do it. Okay, so when I add 0, 1, 1, 1 to 0, 0, 0, 1, it will generate this condition. But we want to see, how we know this condition is generated. All right. Okay. Well, I think most of you can see, what the answer is supposed to be. So I'm going to make this real quick. So it's going to be 0 with a carry. There's a 0 here. So I'm just going to skip a lot of this stuff here. So I'm just going to put, okay, this is a 1. There's a 1 here. 0 here. It's going to look the same here. 0. There's a 1 here. There's a 0 here. And there's a 1 here. Is everybody kind of, okay with this result? 0, 1, 1, 1 plus 0, 0, 0, 1 ends up as 1, 0, 0, 0. But in this case, the overflow flag was set because the sign of the result does not make any sense. What do you mean by the sign does not make any sense? Well, let's think about it. The sign flag it indicates whether a number is representing a negative value or not when we choose to look at it as a signed number. Is this number positive or negative? Or, well, it's non-negative, okay? Okay, so we'll just say it is non-negative. What about this number here? It's non-negative. What about this number here? It is a negative number. How can you add two non-negative numbers and end up with a negative number? The sign does not make any sense. Okay, let's try out another example. So the other example will be going, exactly the opposite way. So we'll go ahead and add 1, 0, 0, 0 to 1, 1, 1, 1. That'll do it. All right, so we'll go ahead and go through this calculation real fast and find out why the sign doesn't make any sense. 0 plus 1 is 1, and there's no carry here. End result is 1 here. This is kind of boring, right? And this is the only time when we have a 0 here with a carry over here, and there's no carry from before. As a result, this is a 0. Okay, now does that make any sense? Does the sign make any sense? This is a negative number. This is a negative number. But the sum is a non-negative number. Hey, we have a problem here, don't we? Okay, so these are the two cases where the sign of the result does not make any sense. The question is, how do I design the gate logic to set the overflow flag when it is the right time to set the overflow flag? That's the question. Okay. Now, in order to perform this operation, I'm going to have to rely on several bits here. So I'm going to look at the sign of the first number as lowercase a. Okay. The other bits are not even important in this consideration. I'm going to look at the sign bit of the second number as b, and I'm going to look at the sign of the sum as bit c here. Okay. So the overflow flag should be expressible using just a, b, and c, and also in combination with some of the logical flags, logical operations, and or not. Okay. So the question is, what am I going to do with this? How do I specify that the sign does not make any sense? Okay, there are only two cases where the sign does not make any sense, and I have already enumerated all the cases. So what you can do is to say, okay, when A is true and B is true, but C is not true, then it does not make any sense. That's one combination. Can everybody read this expression here? A is a 1, B is a 1, C is a 0. Okay, because in that case, the sign doesn't make any sense. I'm adding a negative value to a negative value, but somehow end up with a non-negative value. Okay. And then we have another condition here, which is the flip side of this. Not A, which means the first number is non-negative. Not B, which means the second number is non-negative. But somehow I end up with a negative value as my result. And then you put an OR in between, and that's it. This is how we determine that the sign of an operation or the result of the sign of the result of an addition or subtraction does not make any sense. That's the overflow flag for addition. It has a different definition for subtraction. Are we still doing okay so far with these 4 flags? We are not going to use any more flags in this class. There are tons of flags in the IP86 architecture, but as far as calculation is concerned, we only need to pay attention to these 4 flags. And I'll just go ahead and name those 4 flags again. The first one is the 0 flag. It's easy. If the result is 0, the 0 flag is going to be set or has a value of 1. The second one is the extra carry flag. Okay? Because we don't have a place to store the extra carry flag, it is stored as its own little flag sitting somewhere in the processor. The third one is the side flag. The side flag is probably the easiest one. It's just the most significant bit of the result. And then we have this really kind of complicated one called the overflow flag. The overflow flag is set when the sign of the result doesn't make any sense. Yep.
All function here regarding these things can be like this one here. Is it or using a gate or something?
Or is definitely a gate. I mean, if you want to draw this out, as a gate picture, you can certainly do it, because what you do is you look at A, B, C as inputs, and then you have 2 AND gates here. The first AND gate will take C as it is, but it will negate B and C. Alright? The second AND gate will negate C, but keep the other 2 the same. Okay, so we have this one here, this one going here, and this one right here. And then we have an OR gate. This looks like a happy face. And ruling. That's your overflow line. Rule overflow. It works out.
So basically, these are the conditions, but we have our zero factor.
When this output is a 1, it means the sign doesn't make any sense. The sign of the result does not make any sense. The sign of the result does not make sense. Okay, so I'm gonna stop the discussion here. You might want to read the notes that's already posted, because I'm pretty sure this is covered in one of those links. I cannot remember which one, but it's there. All right, so I'm gonna shut down the recorder and go to the lab if you guys have any questions.